Welcome everyone to day one of the Net Zero for New York Dairy virtual conference presented by Cornell Pro Dairy and Cornell Cooperative Extension. My name is Margaret Quasdorf and I'm the CCE Northwest New York Regional Dairy Management Specialist, and I will be your host for today's program. We are excited to welcome Dr. Frank Mitloehner, Professor and Extension Specialist in the Department of Animal Science at UC Davis. So thank you for joining us today, Dr. Mitloehner.
I'm very excited to be here, and I think this is really a great opportunity to inform you about the stuff that we are doing here at UC Davis, and I think it has a significance to what you do for sure. I was asked to talk about livestock and climate, obviously a broad topic, but one that's really hot and getting hotter by the day, no pun intended. Before I get started, just want to let you know we are on Twitter. GHG Guru is my handle. My center, the Clear Center, is on Twitter. UC Davis Clear. And with that, I jump right into it. So I couldn't talk about livestock and climate without putting a focus on methane. Methane is the Achilles heel in animal agriculture, particularly in dairy and beef. And it will become clear as to why that is. Obviously, ruminants are animals that produce a significant amount of methane. It's belched out, so that's a process called enteric emissions, but also more methane comes from animal manure. And those people who don't like us very much out there say all sources of methane need to be curbed, and that's particularly true for animal agriculture, and here with focus on ruminants. So what's all that talk about greenhouse gases and warming and so on? So here just a little rundown. Imagine the sun radiating down solar beams to the surface of the earth, and with it with that solar radiation, of course, heat. Normally that solar radiation would be reflected back into space if there weren't a blanket formed by greenhouse gases such as CO2, methane, and others. These greenhouse gases, again, I use this analogy of a blanket, form that shield retaining the solar heat in our atmosphere. So without that blanket, without these greenhouse gases, life on Earth would be too cold. We couldn't live here. We need greenhouse gases. But the problem is we are putting too many of those up there, and that means that blanket is getting too thick and we are retaining too much solar heat in our atmosphere. So I think most climate scientists will agree that greenhouse gases are one of the main culprits of this warming impact on Earth. So methane is one of them, and so let's unpack. Currently, methane is by most, not all, but by most places, characterized using the so-called global warming potential over 100 years, called GWP 100. Please remember that. GWP 100. That is a way of comparing gases such as methane and nitrous oxide to CO2. So all you do when you want to know what, let's say, 10 tons of methane do is multiply the 10 tons, let's say from a farm, times this factor, this global warming potential factor, 28, and then you arrive at the CO2 equivalent amount. So a farm producing 10 tons of methane would produce 10 times 28, 280 tons of CO2e. Okay, so that's the global warming potential 100 that has been used over the last 30 years, 30 over the last 30 years by most. One of the rare exceptions in the United States and worldwide is New York. You are not using GWP 100, you are using GWP 20, and that makes methane much worse than depicted on this slide. This is one of the reasons why it's very, very timely for you to learn about what I have to say here today, because if it matters anywhere in the United States, it is in your very state. So GWP 100 is a unit of comparing methane and other gases to CO2. There's an important difference between methane versus other greenhouse gases that's oftentimes not considered and not discussed, namely that methane is not just produced, but methane is also destroyed. This slide here shows the global, I emphasize, the global methane budget. On the left side of this budget, you see fossil fuel production and used agriculture and waste, biomass burning, wetlands, and so on. All of these sources combined emit a total of around 560 teragrams of methane. 560. This is where the story ends in many articles that we read, but it shouldn't end there, because on the other side we also have sinks, meaning there are not just sources, but also sinks, and these sinks reduce methane. And as you see from the second half bubble, the white one, the total sinks amount to 550 teragrams. So we have 560 produced and 550 destroyed, and that leaves us with a balance of 10. Still a number that we seek to further reduce, don't get me wrong. But important to notice, methane is not just produced, it is also destroyed. And if you look at this large arrow pointing down here, it says underneath, sink from chemical reactions in the atmosphere. And what that means is that there are molecules in the air. There are molecules in the air that once they meet methane, destroy it. And that generally happens within a decade. And that is very important to know. Methane is not just produced, methane is also destroyed by these molecules called radicals. To be precise, they're called hydroxyl radicals, and they lead to a very short lifespan of this gas. Again, it's around a decade. And that's depicted on this slide, which compares again these three gases, CO2, methane, and nitrous oxide, but this time based on their lifespan, the time that they stay in the air once we emit them. So whether we burn gas and put CO2 into the atmosphere, which stays 1,000 years there, or whether a cow belches out methane, which stays there a little over a decade, makes a big difference. Okay, this difference is oftentimes not considered, but it should be, as you will see in the next couple of slides. So remember, methane is not a long-lived climate pollutant, such as CO2 or nitrous oxide, but it is a short-lived climate pollutant. Also, biogenic methane, meaning the methane from livestock, has an interesting story behind it that is different from other greenhouse gases that stem from other sources, such as the fossil fuel sectors. I explain. Where does the carbon that's in the methane that's belched out by cattle or coming from their manure, where does this carbon come from? Well, it originates in the atmosphere, from the atmosphere in the form of atmospheric CO2. Plants that are eaten by our livestock take on this atmospheric CO2 during photosynthesis. We all know that plants need sunlight, water, and a source of carbon, and that source of carbon is atmospheric CO2. And these plants then convert that carbon into either cellulose or starch. And then sooner or later, bovine comes along and eats that above ground vegetation, and some of that carbon contained in those carbohydrates is then belched out during enteric emissions, or in the form of enteric emissions. So that methane, and that's the question now, contains, of course, carbon. But is this carbon contained in this methane? Is this new and additional carbon added to the atmosphere? Is the carbon contained in this methane molecule that you see there new and additional to our atmosphere? And the answer to that question is no, it's not. It's recycled carbon, because this very carbon here originated from this very carbon over here. So it changed its form, but it's not new additional carbon added to the atmosphere. And because methane is not just produced, but also destroyed through this hydroxyl oxidation process, a constant source of methane, and I repeat, a constant source of methane does not add new additional carbon to the atmosphere. It recycles existing carbon. A constant source of methane, such as a constant cattle herd, does not add new additional methane, and hence does not add new additional warming. Only if we increase methane, then we increase warming. But if we have, let's say, constant cattle herds, we are not increasing atmospheric warming. This is a sea change in the narrative around methane and climate. I hope that you understand. That's very important. So I told you methane is produced by, let's say, belching and manure from bovines, but methane is also destroyed, and that takes approximately 10 years. The process, again, I repeat myself, hydroxyl oxidation, converts that methane into CO2 where it came from. So you might ask, is that a good or bad thing? Because I just told you that CO2 has a lifespan of 1,000 years. whereas methane has one of a little over a decade. Well, it's not really the question whether it's good or bad, but the question is the carbon that our livestock add to the atmosphere new and additional? And the answer is no, it's not. The resulting CO2 here is not new and additional. It originated from atmospheric CO2 before. And so the biogenic carbon cycle is depicted here and is not just applicable to animals that are grazing, but all animals are herbivores. They eat plant material. And so whether it's forage that these animals graze, or whether it's silage, or whether it's something else that we feed to our animals that's of plant origin, all of that, while it was alive, assimilated carbon from the atmosphere. The only difference between grazing animals and animals in a freestall environment, let's say, where the feed is brought to them, and where some of that feed was grown, is that some of that feed is grown with the use of fertilizers, chemical fertilizers in some cases, and these chemical fertilizers would have had a net addition of carbon. But overall, a constant source of methane does not add additional warming, and this is really important. Is this the same or is it different from other sources of carbon? And we'll get to that in 2 slides. But before I get to that question, I want to show you what the US dairy industry inventory has looked like over the period from 1867 until pretty much today. What you see on this slide here are USDA data. In 1867, we used to have 9 million dairy cows. At that time, we had about 30 million people in this country. We had 9 million dairy cows. At the height in the 1940s, we had 25 million dairy cows. And since then, we went from this 25 down to 9 point something again. So today, with a human population of 330 million people in this country, we have the same amount of dairy cows as we used to in 1867. So today we have 10 times more human people, but we satisfy the dairy needs with the same number of animals. And as you can see here, the trajectory of the inventory went down, 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 and down since the last, 70 years. So it has kind of staggered, it has kind of plateaued over the last, 2-3 decades. But certainly it has not gone up in any major way. And that means that our methane has not gone up in any major way, except for the fact that the dairy industry in some parts of the country has converted from solid to liquid manure storage. And that to some extent has increased methane, okay? But inventories of livestock, of dairy, have not gone up significantly. So that leads us to the question of, does the biogenic methane from livestock differ from, let's say, fossil methane, which by far is, or fossil greenhouse gases, which by far are the main culprit of human impacts on climate? So first of all, what are fossil fuels? Fossil fuels are oil, coal, and gas. Originally, these were plants and animals, such as dinosaurs, that lived, died, decayed, fossilized, and accumulated underground. And over the last 70 years, 70, humans extracted approximately half of that carbon. That's a vast amount of carbon from down there by fracking and drilling and so on. We extracted it from the ground. We burned it with cars, trucks, trains, planes, ships, power plants, cement factories, and so on, and therefore send it up into the atmosphere in the form of CO2, where it accumulates and stays for over 1,000 years. Okay. So this, ladies and gentlemen, is not a short-lived cycle. This is a one-way street from the ground up into the air. And this is the main reason as to why we see CO2 concentrations in the atmosphere going up, 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 and up. Here, direct comparison of the fossil fuel greenhouse gases on the one side, on the left, versus the biogenic carbon on the right. Fossil fuel, as I said, is ancient carbon that was stored down there for a long time. We extracted it, and every time we burn it, we put new and additional carbon into the atmosphere. On the biogenic side, we have CO2 in the atmosphere that's taken on by plants, as I said before, during photosynthesis. Some carbon stays above ground, but the majority goes below ground into the roots and from there into the soil, a process called soil carbon sequestration. And if we leave those soils undisturbed via minimum tillage or no tillage, or grazing, then that carbon is locked away for a good long time. And this soil carbon sequestration is one main means of pulling carbon from the air in and locking it away. Of course, our livestock eats some of that above ground vegetation, and when doing so, produces methane. Some of that is belched out, some more comes off in the form of manure. But that methane stays in the atmosphere for about 10 years or a decade and is then converted back into atmospheric CO2. So we have a one-way street of carbon on the left side. We have a cyclical carbon flow on the right side. So obviously, quite a difference with respect to the total mass balance of carbon, because on the left side, we are adding new additional carbon that was stored in the ground for a long time. On the right side, we are cycling around existing carbon through the biosphere. Colleagues of ours from Oxford University in the UK said, what we are currently doing with methane is just wrong, because we are acting as if methane were simply a more powerful CO2. And 28 or 34 so times more powerful than CO2, and that is depicted in the form of GWP 100. They said GWP 100 is really not an appropriate means of characterizing methane's impact on climate. In fact, it doesn't really characterize its impact on warming at all. It simply converts it into CO2 equivalent units. It does not really, this GWP 100 does not really characterize the fact that methane is not just produced, but also destroyed, that there's an atmospheric removal of this gas. And so they developed a new unit called GWP Star. Those colleagues from Oxford and I, for years, have told the world this old unit GWP 100 drastically overestimates the impact of methane from constant sources on global warming. First bullet point here speaks to that. GWP 100 in our assessment overestimates the impact of constant sources of methane, such as constant cattle herds, by a factor of 4. By a factor of 4. The new unit that was developed by Oxford University called GWP Star actually looks at not just the fact that methane is potent, but also that it's short-lived, that there is an atmospheric removal. And this is a really important distinction, as you will see very quickly. This new unit GWP Star has gained a lot of credibility and a lot of attention over the last few years, and also some criticism, particularly by those who feel that GWP Star is a means of creatively accounting the impact of livestock on climate, even though it has nothing to do with it. GWP Star is based on GWP 100, but it actually accounts for the atmospheric removal of methane and not just its production. I want to get your attention back to the first bullet point here, namely the notion that this old unit GWP 100 that has been used for so long overblows the impact of a constant source of methane on climate by a factor of 4. GWP 20 would be even worse than that, and that's the unit you use in New York. So is that just the opinion of a group from Oxford and us here at UC Davis? No, it's not. To my great satisfaction, I read the IPCC, Intergovernmental Panel for Climate Change report that came out last August. And in it, on page 123, it's called the AR6 report, the Intergovernmental Panel for Climate Change repeated exactly what we had been preaching for a long time, namely that GWP 100, the old unit, overblows the impact of a constant source of methane by a factor of 3 to 4. The point I just made to you is now denoted in the IPCC AR6 report. So you can imagine that this is even worse for GWP 20, the unit that you use in New York. Also, this AR6 report by the IPCC, as you can see here, quotes GWP Star. It's all over the report, and I think that it will, over time, replace the old unit GWP 100 and GWP 20. At least that's my hope, my serious hope, because these units do a particularly poor job in constant and particularly decreasing sources of methane over time. So I will now explain how two gases that are oftentimes compared to one another, CO2 and methane, how they compare to one another. You will find some slides here having references at the bottom so that you can read up more if you so wish. So first, CO2. Let's imagine you were to drive to work on Monday, day one. When you do so, you burn gas and you put CO2, you put carbon into the atmosphere. On Tuesday, you drive again the same distance and you put new additional CO2 to the existing stock from Monday. On Wednesday, you drive again and put new additional carbon through the exhaust pipe of your car to the existing stock from Monday and Tuesday. And to the existing stock you put into the atmosphere last week, last month, last year, last decade, to all the stuff your parents and grandparents put into the air. Remember, CO2 is a long-lived climate pollutant with a lifespan of 1,000 years. Therefore, it accumulates in the atmosphere, and that's what you see here. Currently, this GWP 100, and even worse so, GWP 20, treats methane as if it were a stock gas too, as if methane were accumulating in the atmosphere, just like CO2 does. But does it? The answer is no, it doesn't. Methane is not just produced, methane is also destroyed. As long as you have a constant source of methane, an equal amount of this gas that's produced is also destroyed. And that makes methane a flow gas. Allow me an analogy, a bathtub analogy, one for CO2, one for methane. The CO2 analogy bathtub is one where you have a faucet, but you have no drain. Every time you turn on the faucet, you add water to that bathtub. Whether you turn it on low, medium, or high, every time you crank that faucet up, water levels will rise. They cannot go down because there's no drain. Let's now look at the methane analogy. Here you have a bathtub that has both a faucet and it has a drain, and the drain is always open. Remember that. The drain is always open. The drain is, of course, the atmospheric removal of methane, okay, now an analogy. So if we now turn our faucet in this methane bathtub analogy on normal, then we put water into the bathtub, but all the water we put in is drained out of the drain, and therefore there's no increase in water levels. If we turn the water down, if we turn the faucet down, then because the drain is still open, the water levels can go down because we are putting less water into this bathtub than is let go off through the drain. Only if we crank that faucet on all the way, we could add more water to this bathtub than we let go of through the drain. So that is what happens with methane. We have an atmospheric removal, and we must account for it. That's very important and currently not happening with GWP 100 and particularly not happening with GWP 20, the very matrix you use in New York. I will now show you how this old unit GWP 100 compares to GWP Star under three different scenarios. The first one where methane over 30 years increases by 35%. The second is a scenario where we slightly reduce methane by 10% over 30 years. And the third one is one where over 30 years, we strongly reduce methane by 35%. How would GWP 100 characterize these three scenarios? So this old unit would say that an increasing, a stable, and a decreasing scenario of methane would result in strongly increasing amounts of CO2 equivalent emissions in our atmosphere. When indeed we know that's not the case, because when we hold methane stable or when we decrease it, there is this atmospheric removal that needs to be accounted for and that is not accounted for using this old number. How does this new GWP Star compare to GWP 100? Well, it agrees only with this old unit insofar that if we increase methane, then indeed we add a lot of additional warming to our planet. And we do not want to do that. We do not want to increase methane to our atmosphere. But what happens when we hold stable or slightly reduce methane is that you don't see any blue of the north of the x-axis, and that means no additional warming. But because there's a slight decreasing over 30 years, we see a little bit of blue south of the x-axis, meaning a little bit of negative warming. And negative warming is a fancy word for cooling. If you strongly reduce methane, and I really want to submit that one to your memory, if you strongly reduce methane by, let's say, 35%, you are sucking a lot of carbon out of the air. That is similar to planting forests And forests, as we know, plants, as we know, suck CO2 out of the air during photosynthesis, and that reduces carbon. The same is true when we reduce methane. When we do so, we pull a lot of carbon from the air, generating negative warming, i.e. cooling. Okay, so can this be done? Of course, will be the question that you have. Can it be done that we reduce methane by a lot and get this impact here, negative warming from the dairy sector? And I will get to that in just a minute. First, another kind of technical slide that I think is important to show how CO2 and methane really behave differently in how they warm our planet. On top, you see emissions of two sources. Let's say a power plant over 30 years increases its production of power, and with it, it blows out more and more CO2. Another scenario is one where, let's say, you have a dairy with 1,000 cows, and over 30 years, that cow herd grows to 1,500 cows. That would mean if you go from 1,000 cows to 1,500 cows, that you add new additional methane. And yeah, so now how would this increasing load from the power plant versus the increasing number of cows on the dairy, how would these two impact warming? That's on the bottom here. The linearly increasing CO2 from the power plant would lead to an exponential increase of CO2. Why exponential and not linear? Because it is accumulating source, like I showed you on the previous slide, and not like methane, a flow source. So methane, a constant source, a source of methane that's linearly increasing, would also lead to a linear increase of the warming associated with that methane. If you now have constant emissions from a power plant over 30 years and constant emissions of a dairy, let's say in this case, your dairy now has 1,000 cows, always did, still does, how would these two, the constant CO2 from the power plant versus the constant methane from the dairy herd, relate to warming? The constant CO2 from the power plant would still lead to increasing amounts of warming. Why increasing? Because it accumulates, because of the long lifespan of that gas. But look what a constant dairy source would do. It would lead to constant warming and no additional warming. Why am I always harping on constant warming? Because the Paris Climate Accord is calling for humanity to not raise temperature over another 1.5 to 2 degrees centigrade. It calls for halting additional warming. The way for us to halt additional warming is to either have constant emissions, in which case we don't add additional warming, as you can see in the bottom here, or even better, reduce methane. Because if you reduce greenhouse gases, something very interesting happens. So now let's imagine our power plant over 30 years were to ramp down over time and eventually, because they now want to go to net zero, shut down. What would that do to warming if CO2 were to go down over time and then eventually be shut down? The warming from that decreasing CO2 would still increase because even though we're going downhill with our emissions, we still have an accumulating emission source in the case of CO2. And only when we go to net zero, we are plateauing our warming. So net zero for carbon sources will lead to a plateauing of the warming, but only once we reach net zero for carbon. If we reduce methane, then something really interesting happens, which is an instantaneous impact on our warming. Reductions of methane lead to reductions of warming, i.e. cooling. So when people ask me, Frank, is methane a super pollutant? Then I say, in my opinion, CO2 is a super pollutant because while it's less potent than methane, it lingers in our atmosphere for 1,000 years. And every time we burn fossil fuel, we add additional warming. To me, methane is a super opportunity because if we manage to reduce it, we reduce warming. Can it be done? The answer is yes, it can. Here in California, we have a new law called SB 1383, and this new law mandates a 40% reduction of methane to be achieved over the next, until the year 2030. 40% 40. At first, our farmers went berserk when they heard what was on the docket there, but then they learned that the state of California had something that made it more digestible, so to say, no pun intended. Namely, that instead of using the Kane approach of using rules, regulations, and fines, the state first used the incentive approach of financially incentivizing methane reductions. And so many dairies went ahead and covered their lagoons. You see in the front a covered lagoon. I know in New York you don't have covered lagoons, you have different types of digesters, but this is one approach that's used here in California. Again, it's called covered lagoons, and what you see bulging out here in the bottom right is biogas. And this biogas that normally would go into the air is now capped and trapped, and 60%, 60 of that biogas is methane. And methane, as you know, is flammable, it contains energy. But instead of just burning it and making it into power to be used on the dairy, most dairies now go ahead and convert this biogas into renewable natural gas, which is a fuel type for vehicles. So far, we've had around 100 or so dairies doing what I just said. 170 will be executed within the end of this year. I foresee about 300 or more dairies jumping onto this over the next year or so. So I would say that within the next 3 or 4 years, half of California dairies, or at least half of California cows, will produce gas that will go into covered lagoons. So how did that affect the methane story of dairies in California? Well, we have reduced 2.2 million metric tons of CO2 equivalent emissions annually. And if you ask yourself, is that a lot or not? It is equivalent to 25% less methane from dairy manure here in the state of California. So we will achieve the 40% reduction goal that the state has set forward. And by having such a strong reduction, I just told you we have already reduced 25%, we will achieve this kind of effect here. A strong reduction of methane will lead to this impact on climate, namely negative warming, i.e. cooling. And if you reduce that methane strongly enough, you are net reducing warming on the methane side, which offsets the other impacts of greenhouse gases, such as nitrous oxide and CO2, leading us to a point where the dairy sector in the state will become climate neutral, where the methane reduction will offset other greenhouse gases, getting us to a point of climate neutrality. Not carbon neutrality, climate neutrality. And that's what it's all about, the impact of our activities on warming, on climate. So what does that look like if you take biogas and you make it into fuel? Well, it looks like this. I love this photo. It shows a RNG fueling station. So what you see on the left here is a symbol showing that this is dairy RNG, renewable natural gas. So this is what came from a covered lagoon. It is cleaned up and then it's going straight into vehicles such as semi-trucks or buses to replace diesel. This, ladies and gentlemen, is considered the most carbon negative fuel type there is. And as a result, the state of California has strongly incentivized its production. The so-called low carbon fuel standard credits and RIN credits are the highest of any fuel type credits. They run anywhere between $150 to $200 per ton of CO2e. And not just California dairies are jumping onto this bandwagon, but dairies from other states as well, selling into the California market. This program is guaranteed for 10 years. And I would consider that a new gold rush. I have never seen anything taken off the way that these covered lagoons have over the last few years. So in other words, our dairies are considered by many agencies, but also many policymakers as a solution to our climate issues. You can imagine that there are now activists who are running wild and don't want that. They want to take this down really hard. But we'll see in the next couple of years how all of this plays out. So a little bit broader picture here, US dairy trends already alluded to us having way more dairy cows in the past. We used to have 25 million, today we have 9. So we are producing, with much fewer cows, way more milk than we used to, about 60% more milk today than we used to with a much larger herd. Carbon footprint of a glass of milk has shrunk by 2/3. A story that hasn't been told enough, okay? We must really be careful because people in the anti-livestock arena are trying or are accusing us of using creative accounting, trying to greenwash and so on. You have to be aware that what I'm presenting to you here today is fact-based, is science-based, needs to be communicated in a way that's very careful. Okay, we must never say cows can cool the planet or something like that by reducing greenhouse gases. But what we must say is we are committed to first understanding our impact. Secondly, aggressively reducing our impact further, for example, methane, because if we do so, then we have a very positive impact on climate. And we in agriculture are one of two sectors, which is agriculture and forestry, that have the ability of being a net solution to our climate. So we have to take this bull by the horn, so to say, and run with it and communicate it in a way that is fact-based, clear to the consumer. And I think that is really the challenge ahead. So my colleague, Sarah Place, who is the next speaker, and I have written a white paper that's available on the Clear Center webpage. I will share the link in the chat in just a second. I encourage those of you who are interested in figuring out how beef could become climate neutral to read up that white paper. Also, what I just talked about, the whole methane story is captured in a 5-minute YouTube video that we put up a year ago. I encourage you to go to YouTube and look at Rethinking Methane. Last but not least, there are people out there, and they are supported by much of our media that are trying to sway people to change what we eat. And they are telling the consumer that if you want to make an impact on climate, you need to change what we eat, what we consume. So I already told you that I think the main ways of reducing methane can be achieved through smart technologies, such as manure digesters or feed additives, some of which reduce enteric methane by 10 to 50%. I don't have enough time to go over that during my talk, but we've done some very, very encouraging research on that. So I think that this is really the main angle of attack and not consumption. I do not think that a change of our diet will have a major impact on climate. And some of my colleagues have recently confirmed that. One group looked at what would the impact of switching an omnivore diet to a vegan diet, what would that do per person? So if you, an omnivore, were to go vegan to save the planet from climate change, that would reduce your carbon footprint by 0.8 tons of greenhouse gases. Is that a lot or not? Contrast that to a single flight from the United States to Europe per passenger. That would amount to 1.6 tons. In other words, for me to go vegan, or for me to offset one flight from the United States to Europe would mean, and that's per passenger, would mean that I would have to go vegan for 2 years. The entire country going meatless Monday, as some propose we should, would reduce the United States carbon footprint by 0.3%. The entire country going vegan, 330 million Americans, just theoretically, would reduce our carbon footprint by 2.6%. I would say that's pretty dismal and of course not achievable. And so all this hype around we need to change what we eat, dairy-wise, meat-wise, and so on, is a smokestack that I think we need to be very clear about will not get us where we need to go. By the way, not too long ago, I talked to one of the head figures of the US vegan community, and I asked him, so what is your major challenge as a vegan society? And he said, the main challenge is the so-called retention rate. And I asked, well, what do you mean by that? And he said, 84%, that's 84% of all vegetarians and vegans in the United States stay vegetarians or vegans for only 1 year, and then they stop. And I paused and I said, I guess what you're saying is that for every one active vegetarian and vegan in the United States, there are 5 former vegetarians and vegans. And he said, yes. So the reason why I bring this up is not at all to make fun about that line of, that type of food preference, but just to say a gold standard, veganism, vegetarianism, I don't think so. The most sustainable food consumption pattern, I don't think so. If people don't stick to it, it's not sustainable. Anyhow, if you want to know what the main environmental footprint of our food system is on, overall, then it's depicted very well in my last slide. The slide here shows a US family in front of all the food that's not eaten but wasted. 40% of all the food we produce in the United States, 40% of all the food produced in all developed, and 40% of all food produced even in developing countries is never eaten. In the developed world, mainly because consumers don't finish up or throw away what they think is no longer good. And in the developing world, it's mainly not at the consumer, but at the producer level, because farmers can't harvest on time, transport the goods to the markets or distribute and so on. But 40% is a global number that I think all of us can agree upon is unacceptable and needs to be changed. And that includes our sector. So thank God we are, the animal sourced food kind of food sector is the least wasted, is the sector with the least wasted commodities. The ones with the most wasted commodities are the perishable foods, and that's fruits and vegetables. 60% of those are wasted, 10 to 20% animal source foods. So with that, I come to close my talk, and just want to point out, if you're interested in any or whatever I said here, the CLIA Center has a blog and many explainers and YouTube links and so on. I think for those of you interested in this general topic, you will find a lot of good stuff on there.